Hi everyone, we're going to wrap up chapter 4 quickly because I like to concentrate on things that are um, difficult to process or you need it introduced in another way. But this stuff is pretty simple when we talk about placement and locations of telescopes. So we're going to run through this. Telescopes we've learned all about. Observatories are places for telescopes that also have infrastructure to protect them and that have instrumentation that are associated with telescopes. So those are observatories. They can be on Earth or they can be in the atmosphere or they can be in outer space. But the location is important on Earth, especially because we want to avoid light pollution, which living near New York City, you know everything about. But we also, for radio telescopes, want to avoid radio pollution. And in fact, the largest radio telescope that is steerable in the United States is in West Virginia. And for, I think, like 40 miles on a perimeter around the telescope, you cannot have wireless internet. So they use modem internet during COVID to get all their assignments back and forth. But that is to minimize the radio pollution in that area, which is a big issue for them. When we talk about the instrumentation that is associated with observatories, we're talking about imaging systems and photometers. And in terms of those, in regard to imaging systems, that is, and I think I have another slide here, so I'm just going to back it off. No, I don't. Wow, I must have taken that slide out. I can do it anyway. For imaging systems, those are basically photographic plates. And they've moved from film to digital, so they are more sensitive, but they aren't as sensitive as they need to be, although they can create optical images. And so they are combined with photometers, which are highly sensitive to, and they are essentially light meters that are embedded digitally along with that. Combining them, the two of them together, they're put into what's called array detectors. And array detectors combine the imaging and the photographic plates with the photometers as well, so that you can cover more wavelengths within the visual spectrum, within the ultraviolet spectrum, and more precisely within that spectrum, so that, and you can do it more sensitively, so you can get the intensity of those waves as well. You can also classify the photons coming at you in terms of their wavelengths and in terms of their intensity. And you can digitalize everything so you can analyze it later or manipulate it so that you can put in colors and take out noise. These are often joined, the array detectors are often joined to spectroscopy instruments so they can identify the source of the waves, and they can identify the elements and the compounds that are a part of those waves. Very important to our research for Big Bang Theory. So let's get into that a little bit more in terms of the array detectors and their coordination with spectrographs and spectroscopy. So to go over that a bit more, it's as though these spectrographs have very accurate prisms for not only visual light, but they have very accurate prisms for ultraviolet light, and prisms for infrared light, and prisms for some of the radio waves as well. And in terms of that, they don't use a prism so much as they use grating. And I'm trying to make up an experiment so you can see how that works for grating, to really stretch out the spectrum so that we can get a good feel for where the spectra is strong, and we can identify that as a signature of an element that is emitting light and energy in outer space, or maybe a compound that is emitting lighter energy out of outer space. This is part of what went into the awareness of phosphine that has recently been seen off of Mars. It's all spectroscopy. It's looking at what is coming at you in terms of energy and very precisely looking at the signature spectrum for that element. So we will go more in depth into spectroscopy and the signatures for elements and compounds in the next chapter. For now, I wanted to concentrate on the location of these scopes and these detectors and what we can find there. So if we start at the very short end of the wavelengths and go to the longer ends of the wavelengths at radio waves, then we are starting at gamma rays. And in starting at gamma rays, you know that these are very, very high frequency waves, very short wavelengths, and the highest energy radiation that we can detect. Maybe there's higher, we don't know at this point, and they penetrate mirrors and lenses. So they have so much energy, they just burn right through them. This particular graphic came out of the Fermi satellite, which has array detectors for gamma and for infrared and for visible light. So it doesn't need to use mirrors. And it was able to detect this remnant of a supernova by using those array detectors and spectroscopy. Let me keep going. Oh. X-rays, I'll take that other one out. X-rays. X-rays are also very high energy light, not great with mirrors. So the mirrors need to be redesigned for X-rays if you want to use mirrors. You can use array detectors instead. If you do redesign the mirrors, they have to reflect at a very shallow angle so that you can spread out the power and then focus it into an array detector. So these X-ray telescopes are far above Earth and the atmosphere, and obviously gamma rays are far above, into outer space, because gamma rays are absorbed completely by our atmosphere, as are X-rays. So these are far out in space for these particular probes. This is X-ray, one down, and by looking at X-rays, we often see heavy elements in here. Remember, we talked about the periodic table. We talked about the fact that the sun can fuse elements from hydrogen to iron, and most of it is helium. But for the heavier elements, the sun doesn't have the power to fuse those. But we still have heavier elements, and we're made up of heavier elements. In fact, our Earth is made up of heavier elements that came out of the Big Bang. By looking at X-ray spectra, we can determine, this is out of Cassiopeia, we can, the supernova there, we can determine that maybe these heavier elements came out of a massive explosion right around the Big Bang, and we can look into the origin of our universe out of X-ray spectra. The Hubble telescope, which is far beyond our atmosphere, observes near UV, one up, and visible, and near IR. And that telescope, you see it here being launched out of the space shuttle. It's been through a lot. So it's been repaired multiple times. It's on its last legs now, and it's waiting to be replaced by James Webb telescope. But for now, we'll take what we can get out of it. It features some large mirrors, 2.4 meter, a 2.4 meter mirror, but it also features the ability to collect near UV and near IR light as well. Here's the ultraviolet light. We're going from shortest to longest waves. and we were able to see more supernovas, gather more information about the origin of the universe. And this is a galaxy out here that it really did a great job on. Now that great job has been a while in coming because there were so many repairs that were done to Hubble. In terms of UV, when Hubble looks at the sun and you think, well, that looks ultraviolet. No, the sun is not emitting ultraviolet rays that turn it blue. This is assigned this blue by the intensity of the ultraviolet that is coming out and picked up by Hubble on this spectrograph. So this is a UV image versus a visual image that deals in different wavelengths of light that are assigned colors. Now, in terms of the visual imaging, Hubble was able to give us detail that we've never seen before. This is an optical image from the ground, and this area, which is just so indistinctive, is blown out by Hubble to show this beautiful detail that we were never able to see from the ground. Now, Hubble can also do IR imagery, which is a step down, and it can look at other planets and other moons to do a visual look and then do an IR look, which can really get past a lot of the atmosphere to give us more detail. Here's a visual look of a nebula, and then you see in here this beautiful IR look instead that gets past all the gases. So sometimes the IR can really show us an entirely different image. IR telescopes can go up in high altitude balloons. The James Webb, which will be going up and going farther out in the universe, will also carry IR spectrographs on it as well. Now, for the far IR range, that is range that is getting into microns. We're out of nanometers. Microns are 10 to the -6, so we're moving longer. That would need to be done high above our atmosphere as well, because our atmosphere absorbs those infrared waves around that measurement of 30 microns. And in order to move those scopes up into the atmosphere where it is very cold, we still have to cool the telescope and provide coolant so that the satellite isn't running warmer than the waves it's trying to measure. So that becomes very interesting. It was really an issue with Voyager. Voyager ran out of coolant. So Houston changed up its mission so that it didn't need to look at IR imagery anymore after it ran out of coolant. They have limited lifetimes for those particular probes. And finally, to radio telescopes. We've already touched on this quite a bit. This is the one in West Virginia that I was talking to you about. It's the world's largest steerable radio telescope, which is a big help because the one in Puerto Rico sits at 300 meters and the one in China sits at 500 meters, but they have to wait for the exciting things to go past them because they can't move to the exciting things. And if something exciting is happening out of their range, tough luck. So to have a steerable radio telescope is a huge asset, and it has a very large parabola, certainly not 300 meters though. In terms of that, that's what I was talking to you about. And in terms of radio telescopes, they're so advantageous because they can go 24 hours a day. And that really impacts the amount of work that you can do on them. And the fact that clouds and rain and snow, no big deal, not an optical issue. The radio waves go right through all of that interference. You can also do interferometry across hundreds of kilometers because you have these longer wavelengths to work with. So there